Okay, so we'll see if this works. Hopefully it does. All right, so as I was saying, the logarithmic function is a function that is the inverse of the exponential function. That's what we graphed on the first side. And as I was saying, that basically the important piece is knowing the base, because the base of our exponential function should be the same as the base of our logarithmic function. So we started graphing this 2 to the x function. Oh, that was really loud. All right, let's switch mass break. So I'll do second row and fourth row. If you guys want to take a break, you can. So if we're starting off graphing this 2 to the x, the base of our exponential function is 2. So when we graph its inverse, or the logarithmic function is also going to have a base of 2. So you'll notice that this 2 is kind of like a little bit like below the logarithm. That's called a subscript. And that should be written as like a number that's not like, it shouldn't be saying like log 2x, it's log base 2. So it should be a little bit below your log function. And the way that we read this log with this little 2 and x, we read that as log base 2 of x. So the logarithmic function is generally kind of like shortened to just log. And we say that that's log base 2 of x. And again, the base of the logarithmic function is going to be determined by the base of the exponential function and vice versa. So if the base of the log is 3, then we would start with a 3 to the x. If we started with like a 4 to the x here, your base of your log would be 4. So it's just going to depend on each other, really. Okay, so we're going to look at an example of like how to kind of start graphing these log functions. And I kind of gave you guys a little bit of a couple of steps written out down at the bottom. So we'll kind of just look at a basic log function, then we'll look at some with transformations. So graphing basic logarithmic graphs, we want to start by making a table of values for the parent exponential function. And then we're going to pretty much follow the steps that we did on the last problem. We're going to switch the x's and the y's to get our inverse table of values, which is going to be our log base whatever function that we're going to graph. And then we'll look at the domain, range, and end behavior. So let's start off with this log base 3 of x. So this is a pretty simple logarithmic function that we want to graph. But first that we want to do is start out with the exponential function table of values. What would be the base on our exponential function here? What would be the parent exponential that we would want to make a table of values for? Yep. 3 with the exponent of x. So like I was saying, this base of this logarithm is going to determine the base of your parent exponential. So since we have a base 3 logarithm, we want a base 3 exponential. And to get the table of values here, again, I can still use the x values, -2, -1, 0, 1, and 2. But since we're now working with a base of 3, to get our tables, we would want to raise 3 to the -2 power. Yeah, I'm screen recording, so I will record these notes for those of you at home. Hopefully it will unfreeze itself. It says I'm still recording, so. Okay. And then I have 3 to the -1, 3 to the 0, 3 to the 1, and 3 to the 2. That's how we would get the y values. Again, you're just taking these x values and you're putting them into the exponent on that exponential function. So I think that would give us 1/9, 1/3, 1, 3, and 9 for the parent exponential. And then to get the parent logarithmic function, the logarithmic function is just going to be our log base 3 of x function. Again, that 3 should be kind of written like, sorry, should unfreeze here. That 3 should be kind of written below as like a subscript. So to get the logarithmic function, all I'm going to be doing is taking this table of values, and I'm literally just going to be switching the x's and the y's. So my x values are going to become 1/9, 1/3, 1, 3, and 9. And then the y values are going to be the -2, -1, 0, 1, and 2. And this is going to be what the table is that I want to graph. In this case, when I'm just graphing the logarithmic function, I don't need to graph the exponential function table as well. I'm really just worried about graphing the logarithmic table. So this is going to be the only thing that I'm going to graph here on my coordinate plane here is going to be this table on the right. You're going to kind of have to probably estimate a little bit with those first couple points. And you'll notice that when you put your points in, it should look something that looks pretty similar to the inverse function that we graphed on the first page. And what's going to happen here is we're also going to have a vertical asymptote of this one. And in this case, our vertical asymptote is still going to be the x is equal to 0 line. Because if you notice that, that's kind of where your points are getting really, really close to over here on the left side. Yes.
So for the vertical asymptote, we don't have to do the dash.
Yeah, I was going to say that was going to be my next point. So yeah, you do want to make sure to include your vertical asymptote in your graph as well. So as your dashed line, I know it's kind of hard to do on these axes, but do your best. So similar to what we did with the exponential functions, I would, on a checkup or a quiz or a test, I would be looking for you to put that line in there, that horizontal asymptote as the dashed line. I'm sorry, vertical asymptote. I think I said horizontal. I meant vertical. And while I'm at it, I'm also going to just put in the equation of the vertical asymptote down below. So remember that vertical asymptote should be written as x is equal to, and in this case, our vertical is going to be x is equal to 0. Will it always be? No. Depending on what the transformations of the function are, it could change. So it doesn't always have to be 0. It can be, but we'll see that that might change on the next couple of examples. But what can we say about the domain of this log base 3 of x function? Yep.
0 to 1, 0 to 1.
Yep, 0 to positive infinity. How about our range? Ava? Yeah, negative infinity, positive infinity. So domain starting at the asymptote going to positive infinity. The range is going to be all real numbers. And then we'll look at the end behavior of this graph, which again is going to be a little bit different than the end behaviors of our exponential graphs, but we still want to look at it from the left and from the right. So my left end behavior, if you look on the left side of the graph, this is where the asymptote is going to come in because the asymptote is on the left side of the graph. So we want to say as x is approaching, in this case, our asymptote, which is going to be 0, because that's the x value that we're getting really, really, really close to. So as x is approaching the asymptote of 0, what's the branch doing? Negative infinity. So on the left side of our graph, our x is approaching 0 and our branch is going down. So our branch is going to be approaching negative infinity. And then the right side of the graph, what are our x values approaching on the right? Yep, infinity. And what's our branch doing? Yeah. So right side of the graph, our x values are going to infinity and our branch is also going to infinity. So the right side, infinity, infinity. Generally, you'll see that 99% of the time that will happen. Sometimes it might be a little bit different depending on what the graph looks like. That might change with like a reflection or something of that nature. So yeah, just be careful of that. So that's just kind of the basic log-based something of x, kind of deal with that. When we start talking about transformations in terms of a's, h's, and k's, that's where things might change a little bit. So we'll see that the vertical asymptote always doesn't have to be at 0. It could be, but it might change. And we'll start talking about some stretches and movements and that kind of stuff. Questions on anything so far, though? Okay. So let's look at a transformed. So before we even talk about the graphs using transformations, I just want to give you kind of the general logarithmic function in terms of a's, h's, and k's, just so that we can kind of compare to what we have written as our examples. So I'm going to give you guys the general, what did I call this in my last notes? General logarithmic function. Seems like everything's being slow today. All right, so our general logarithmic function with a's, h's, and k's, we would say is some function f of x is equal to a times the log of some base b. So again, that b is going to be dependent on what the parent exponential function is going to be. So in the last example, we looked at a base of 3. And then you'll notice that in this example, next to the base, there's like a set of parentheses. This is where your h value is going to be found. So I'm going to write this as in parentheses, x minus h. And then our k value could either be added or subtracted at the end, depending on what the sign of it is. So a times log base b of x minus h, and then plus k. And the A, H, and K still do the same things: stretches and shrinks, reflections, left, right, up, down. So let's talk about this particular example. What's our A value here for this first example? Yep, 1. What does that tell us about a stretch or a shrink? There isn't one. So our A value is 1. So in this case, we have no stretch or shrink. That also means that since our A value is positive, there's also going to be no reflection. So log functions can still have reflections. And again, that's just going to be dependent on the sign of the A value. So if A is negative, there would be a reflection. But in this case, there is not. What can we say about our H value here? And what does that do to our function? What's our transformation? Yep, H is 5. So we would say that that's 5 units to the right. Some people are still having trouble identifying this H value, which I noticed on the quizzes when I was grading this weekend. So make sure you know what your H value is. How about K? What's K and what does it do? Yep.
Shift 3 units up.
Yep. So K is 3, so we are moving 3 units up. So how does this transformation of a shift 5 units right and 3 units up affect what we're going to be doing in terms of our tables? Well, let's see. So our parent exponential is still going to be whatever the base is here. So if you notice our base is 3, our parent exponential is still going to be f of x is equal to 3 to the x. We want to start off with graphing the most simple parent exponential function. So whatever your base is should be the base of your exponential. We actually did this table on the last example, so I'm just going to go ahead and just rewrite what we had, which was, I think, 1/9, 1/3, 1, 3, and 9. Parent logarithmic, again, is just going to be this table of values switched, and the parent logarithmic function is just going to be the basic log base 3 of x function, which is exactly what we just graphed on the last page. So that had x values of 1/9, 1/3, 1, 3, and 9. That had y values of -2, -1, 0, 1, and 2. And then this last table is going to be where the A, the H, and the K are applied. So the first two tables are still going to be just the basic, what's the parent exponential, what's the inverse, and then you're going to apply your H and K depending on what you have. So in this case, our translated logarithmic function is just going to be this graph that I gave you the equation of above, log base 3 of x minus 5 plus 3. And this is where I'm going to make the x values move and the y values move. So in this case, since our h value is 5, I want to take my x column and I want to add 5 to all of those values. And the nice thing about this is when you have an addition of like your x values and you have fractions, because we want to graph them, it's kind of a nice, easy way to determine what those values are going to be. If I want to take 1/9 and add 5 to that, well, that's really telling me that I'm really graphing 5 and 1/9 here. If I want to take 1/3 and add 5 to that, I'd really be graphing 5 1/3. So with the addition ones, it's pretty nice. You can just write them as mixed numbers because you're going to want to know where they're going to fall in your coordinate plane anyway. And then the other values should be pretty straightforward. If I add 5 to 1, it'll give me 6. 3 plus 5 will give me 8. 9 plus 5 will give me 14. So 5 1/9, 5 1/3, 6, 8, and 14 for my x values. And in terms of the y values, I know that my a value is 1 and my k value is 3. So what I'm really doing is I'm multiplying all my y's times 1, and then I'm adding 3 to them, which really means that I'm just taking all my y values and adding 3 to them. So -2 plus 3 will give me 1. That'll give me 2, 3, 4, 5. And again, the only graph that I'm really worried about seeing on your coordinate plane is really just going to be this last column. So I really just want to see that translated logarithmic function. You don't have to graph the parent exponential or the parent log. I really just want to see this one here. And again, with the first couple points, you're just going to kind of have to estimate where they're going to be. think that last point is probably going to be off here somewhere. And once you have your points in, again, kind of the upper part of your graph should be pretty obvious of kind of what that behavior is doing. On the kind of bottom part of the graph here, again, we have to be kind of thinking about the fact that we're going to have a vertical asymptote somewhere. What does it look like our vertical asymptote will probably be here, Eva? Yeah, it'll probably be like x equals 5 because that's what these kind of values are pretty close to. So I'm just going to go ahead and actually dot that in just so that I make sure I'm not hitting that when I actually graph in my line. I'll continue my graph downwards. While I'm at them, I'm actually going to go ahead and write that equation of the vertical asymptote in down below. So x equal to 5. And for the parent or for the exponential functions that we were graphing, we said that the horizontal asymptote always had to do with the k value. What do you think about the vertical asymptote in these logarithmic functions? What value do they have to do with? Probably. Yeah, the h value, right? If our vertical asymptote here is x is equal to 5, that's our h value. So for the graph of the inverse functions or the graph of the logarithmic functions, our vertical asymptotes, once you know what the h value is, you should be able to determine where your vertical asymptote is going to be without even having to graph it, which is going to be nice because then we actually have a starting point of where our graph should kind of be working off of. So anytime that we're graphing a logarithmic function, vertical asymptote is going to have to do with our h value. All right, I'll fill in my domain and my range quickly here. So our domain should be our asymptote, which is our x value of 5 to positive infinity. Range should be all real numbers. And we'll talk about our end behavior. So in terms of our end behavior on the left side of our graph, what can we say about that side on the left? As x is approaching what, f of x is approaching what? Eva?
5.
Yep, as x is approaching 5. So as our x values are approaching our asymptote on the left side, our branch is going down. So f of x would be approaching negative infinity. And what do you think we'd say about our right side? Yep. Yeah, both of them are going to be positive infinity. So as x is approaching positive infinity, our f of x is also going to be approaching positive infinity. So what I'm going to have you guys do is I'm going to have you go through and try your hand at this last example. So I'll have you go through and fill in the transformations. I do just want to just make sure that we're good on the same page for the parent exponential. For this example, 2 log base 4 of x plus 6 minus 1, what would be our parent exponential here? Would be what? What's our base of our log? Yeah, it'd be 4. So here our parent exponential would actually be f of x is equal to 4 to the x. So remember that we are looking at that base. The base should be the same here. So when you make your parent table of values for this exponential, you should be using the base of 4. And again, for this one, you can still use the same x values, -2, -1, 0, 1, and 2 to get your y values. You're just plugging those into the exponent. And then that would make your parent log a log base 4. So I'll have you go through, fill in the transformations, fill in your parent log function, do your transformations based on your A's, H's, and K's. And while you're working, I'll go ahead and do my work up here as well. And just a reminder, as you guys are kind of going through and doing the transformations, which I know we've kind of gotten away from transformations a little bit, but remember that when you do have a stretch or a shrink, you should be noting by how much it's stretching or shrinking by, which a couple people had missed on the quiz. So for this particular example, for the a value of 2, you should be writing vertical stretch by a factor of 2, or if it was a shrink, vertical shrink by a factor of 1/2 or whatever. So make sure that you're also practicing writing those things. Okay. And as you guys are finishing up that example, or if you're still working on that, I am planning on doing probably a 1 question type checkup that'll kind of have this format. I'll give you guys a function. I'll have you identify the transformations. I'll have you fill in the 3 tables of values, graph the function, and then fill in that last kind of piece of information down at the bottom. That'll be on Wednesday when we come in. So just kind of heads up on that. And for the homework, for those of you that are in here, that is the last stapled page in that packet I gave you. So there's 4 graphs for you to practice. 3 of them are pretty similar to the ones that we did together in class. One of them, number 3, I think, has a base that is a fraction. So remember that you can have fractional bases when you are working with exponential functions. We did definitely talk about those. And there is also a reflection on that one. So your graph might look a little bit different, which means that your domain could look different and your end behavior could look different on that one. So just be careful on number 3. Are there any questions on anything on that last example or anything that we did in class today? So there's about 7 minutes left, so you guys can definitely get started on the homework. You should be able to at least probably knock out at least one of those graphs if you haven't started that already. I am going to stop screen recording. And I will post this video later on today. I probably won't get to it